Here we have a problem where we're saying Christine runs on her sled at 2 meters per second. She hops onto the sled at the top of a 5-meter high, very slippery slope. What is her speed at the bottom? So trying to visualize this problem, we're going to say there's a top of a hill, and then there's the bottom of the hill. And we're told that this hill is 5 meters high. And so she's running at the top. She's got her sled with her. She's going to jump on the sled, ride the sled down, and then she'll be sliding along at the very bottom. So this is a sort of situation where we're looking at her motion over the whole range of her motion. So this is a good example for us to use a conservation of energy. Basically, her motion is going something like that. What we're going to do is look at an initial point, and we're going to look at a final point. Look at what her energy is at either of those. We know that her total energy has to be conserved. There's no other forces acting on her besides gravity, etc. So what we'll do is look at the types of forces and the types of energies that are present in this system, and then we'll discard the ones that we don't need. So this is our conservation of energy. We have kinetic energy, gravitational energy, elastic potential energy, and thermal energy. In this case, there are no springs present, so we can go ahead and discard spring potential energy. We don't have to consider that here. We're also told that it's a very slippery slope. That is suggesting to us that there's no friction in this situation. But we do know that she is moving. She's moving at the top. We want to know how much she's moving at the bottom, so we need kinetic energy. We know she's moving up and down, so we need to consider gravitational potential energy. If we're going to consider gravitational potential energy, we need a reference point for gravitational potential energy. We need a reference height. I prefer to always pick the lowest point of her motion as the reference height. That means that the gravitational potential energy is always positive, is always bigger than that. And thus you avoid having negative signs floating around that sometimes can be lost or can be forgotten about, that can lead to small but significant errors in our calculations. So here we're going to call the ground, the bottom of the slope, as our zero gravitational energy, and we'll measure everything upward based on this lowest amount. In this situation, this is her height at the end, and so we can also throw out gravitational potential energy at the end. So now we can go ahead and start plugging in what we know. Her kinetic energy is going to be 1/2 mv squared initial, plus her gravitational potential energy is mgy, or it's the initial height that she's at. Her final kinetic energy is 1/2 mv final squared, and her final gravitational potential energy, we said, was 0 height there, and so the whole term goes to 0. One thing that we notice here is that there's a common mass that cancels out in every term. We know that she initially is going at 2 meters per second. We're given that. And we know that she's initially 5 meters above the top, or 5 meters above the top of above the bottom of the slope. When she's at the top of the slope, she's 5 meters above the bottom of the slope. And we don't know the final velocity. That's what we're trying to find. So we have 2 joules that are in her initial motion. We have 49 joules that we get that are released because she's going downhill, so that gravitational potential energy is released, and that's turned into kinetic energy for her. And we find that her velocity at the bottom is 10.1 meters per second. So it doesn't matter what the slope of the hill is. We only care about how high she was and how much she's moving up or down in the y direction, in the vertical direction. She's moving at the beginning and she's moving at the end, so there's kinetic energy at the beginning and kinetic energy associated with that motion at the end. We conserve everything, we set everything equal, and we can find her total velocity at the end.